Yeah, so our next talk will be given by Laura Šerkšnytė, whose last name I pronounced correctly. um, yeah, so as you can tell by the name, she's pretty much a local, or was a local here. She finished her bachelor's here in 2017, and then went off to study in Munich. Yeah, and then in 2019, she joined the ALICE collaboration, and then a bit later in 2020, she joined the CERN. She started her PhD. And now, as of November, she's a research fellow at CERN. She already has 2 awards for her work and also a Nature publication. So she's really Nature Physics publication. So she's off to a really good start. And I guess the talk will be just as good. Yeah, so enough of me talking. Please welcome Laura to the stage.
Okay, now my mic is on. So I prepared all this introduction about telling how I'm Lithuanian and how I did my bachelor's here, which was just said. But yeah, I wanted to say all of that story to just say that I'm very happy to be back. The 4 years here were very nice. I always remember it with a smile, and thanks for the organizers for inviting me. What I will talk about is a little bit bridging between the physics we have at LHC and physics we have in our galaxy. So I will talk about Antihelium-3, which we produce at LHC, but we also hope to observe it in our galaxy. And before I go into the physics, I made yesterday a slide on open readings because actually I used to organize it myself 10 years ago. It was a lot of fun, and what I wanted to say with this is also thank you for the organizers who keep doing it. You're also doing a much more professional job than we did 10 years ago, so guys, very well improved. And okay, so what we do at LHC is called fundamental physics, so we don't produce usually things, or at least that's what people think. In principle, we do produce things because we have to develop detectors that don't exist yet to do physics that also is not understood yet. So there is this entire detector development part, which I will not talk about, because as a research scientist, what you do is the fundamental physics. And one of the things we can ask ourselves is indeed, what is the world made of? And this is something you study also during your bachelor's. And you learn that objects are made of molecules, molecules are made of atoms, and then atoms are made from nucleus and electrons. And the particles and systems I mentioned up to now is something that really makes up the matter around us, and these are the ones we are used to. But there are a bunch of particles that don't exist around us in a let's say, daily life, and you have to either produce them or get them from somewhere else. Before I go into more details of that, I want to show one of the examples of a particle which was first predicted by theory and only then observed. And the story starts with the electron, actually. Okay, now I need to figure out how this works. Wait. Now, oops, sorry. Okay, I can control it. So it starts with the electrons because there was a theorist called Paul Dirac who wanted to develop an equation to explain an electron. And he succeeded. He developed the so-called Dirac equation, which has several solutions. And some of them result in an electron, but the other ones result in an electron with a negative energy, which does not make much sense. So after some thought, Paul Dirac said that what we expect to have are particles which are exactly like electrons. So for example, they have the same mass, but they have the opposite charge. They are positively charged electrons. And this was the first idea of antimatter. However, it was so new that most of the other scientists said he's wrong. It's not possible. And then what the job of the experimental physicist is to try to look for those particles and see if we can really observe it in nature. Because theory can tell many things. At the end, the experiment tells if what is in the theory is correct or not. And to see the positrons now, it's rather easy. You can go to LHC, to the Large Hadron Collider, collide particles with high energy, you produce a bunch of new particles, and of course you also have positron there. However, at the time, they did not have accelerators, so you had to find a different way where you expect to produce these particles, and this is where cosmic rays come into play. So cosmic rays are these very high energy particles that are propagating in our galaxy, and they also attack Earth in a sense. So they really come to us and they hit Earth all the time, and they hit our atmosphere all the time. If you have high energy cosmic ray hitting the atmosphere, it interacts with the matter there and can produce these so-called showers. And by now we know that in those we can also produce the positrons. And the discovery of cosmic rays was done by Victor Hess in 1912, and later he got a Nobel Prize for it. Now, once we know we have these cosmic rays and we might have the positrons there, we also need to have some sort of a detector where we could actually see that one of those many particles coming towards us is a positron. And this required another development, which at the time what they use is a cloud chamber. So you have basically a box. You fill it with the supersaturated vapor of water or alcohol, and what happens is that when your particles traverses the gas, it ionizes it, and you can basically follow a track of how your particle moved in space and take a picture. And this was another development in particle physics, or in this case more detector side of particle physics, which got a Nobel Prize. And both of these things were necessary to come to the point where experimentalists could say, yes, positrons exist, and Dirac was actually right. And what Anderson did, which is another scientist who also got a Nobel Prize together with Dirac, well, at separate times, but they both got it, is he used this cloud chamber. He put it into a magnetic field, because if your particle moves into a magnetic field, it bends, and you can know then the charge of the particle. And he also put this lead plate, because the fact that you know that the charge is +1 doesn't tell you if it's a proton or if it's a positron. So they put the lead plate, and they see how much energy the particle loses. And the proton would lose much more energy than we see here for the positron. So, okay, this was the first ever observation of an antiparticle. And by now we know that we have particles, we have antiparticles. Many more discoveries were done and developments of the theory. And all of them converge to the standard model of particle physics. In the standard model of particle physics, you have these elementary particles that you can see here. And first of all, you have quarks. We never observe them alone. We always observe them in a sense in bound systems. And quarks are the particles which make up protons. So you can see here in a sketch that proton is made from UUD quark. Then leptons, for which one good example is the electron that you all know. And then finally, we have other particles, which we call force carriers. So for example, the quarks, they can interact via the strong interaction, which happens via the exchange of a gluon. And then gluon is known as a force carrier for the strong interaction. Then we can ask ourselves, is this the full story? So it is a full story in a sense that what we observe so far in LHC, we can explain very well with the standard model. But if this is all that we need to know, we should be able to explain also larger structures in nature, and we can go back to bigger scales, to our galaxy or even our universe. So we can look at objects we see in the sky. For example, the spiral galaxies which rotate. And the idea is if our physics is right, we should be able to explain how they rotate. So what astrophysicists can do is they can measure how fast the matter rotates dependingly on the distance from the center of that galaxy. And what they would obtain is something like this white curve. Now, of course, once we measure something like this, we want to understand, is this what we expect? And what one can do is one can measure how much matter we actually have in that galaxy, do the calculations based on gravity, and see if we obtain what we measure. And what they obtain when they do it is this dashed line, which is much lower velocities. And this is not understood. So this could be assumption that maybe we don't understand gravity that well, but this is not a very popular solution. What people usually say is that there should be matter in the galaxy which we don't see, but which interacts gravitationally. And now we call it the dark matter. Since, okay, most not likely not, since a while, we have many different observations which require dark matter to be explained. For example, gravitational lensing, or you can even observe how galaxies collide and see how matter is distributed in that collision. And even there you see that the explanation requires the dark matter. By now we also know, I don't know why there are no numbers, okay. By now we also know that ordinary matter makes up 5% of our universe, and dark matter makes up around 27% of our universe, and the rest is dark energy, which I will not touch in this topic at all. Now, the dark matter itself, we think by now that it should be a particle. However, it has never been observed so far, and there are several ways how people around the world are trying to do it. And usually we depict it in this sketch here. So how you have to read it is that the pink blob just tells us some physics happens, some interaction happens in here. Then you have the two standard model particles and two dark matter particles. And then we can read them in different direction and go through different processes. So for example, if we go from right to left, we see that we have two standard matter particles which interact and in final state have the dark matter particles. These are searches that are done at collider experiments where you really collide particles, you measure everything you produce, you see how much energy you have, and then you see if there is any missing energy compared to energy you put inside of the collision. Another way to look is if we go from, for example, from the bottom down, sorry. Okay, if we go from the bottom up, and then we have dark matter particle interacting with standard model, which remains dark matter and standard model particles. And here the searches, how they are done, you basically again have like a big chamber of gas inside, and you hope that the dark matter from the galaxy will hit your detector, will interact with the nucleus, and the nucleus will have a kink. They call it nuclear recoil. And then finally, you can also read it the other way around. You can read it from left to right, which means that you have dark matter particles interacting, and in the result, you have standard model particles, which we can detect. And it is called the indirect detection because you don't look directly at dark matter, you look at the product that appears once dark matter interacts with each other. And this is the topic we will touch today in more detail. So when the dark matter annihilates, it can result in any, in principle, standard model particles, including, for example, gamma rays, neutrinos, and antimatter. And all of these are now used to search for the dark matter. But today, we will discuss only the antimatter case. So you remember I said that electron has its antimatter particle, a positron. In the same way, proton has an antiproton, which has the same mass but opposite charge. And you can even form the bound nucleus, for example, antihelium. So in helium-3 case, you have two protons inside and a neutron. In case of antihelium-3, you have two antiprotons and antineutron. And indeed, later on in the presentation, you will see it denoted as helium with a bar above it. So now we come to the same problem as we had with the positron. So I really like this positron example, and we will come back to it very often. In case of positron, we didn't have colliders at the time to produce positron. Now we also don't have colliders that would collide dark matter particles so that we could look for this antihelium. So we need a different way. And this is where we come back again to the bigger scales, and we go back to our galaxy. Because in our galaxy, we also have dark matter particles. And the idea here is that in the sketch, you see a simple representation of our galaxy with the solar system here and Earth here. So what happens is that dark matter annihilates in our galaxy. It propagates it produces antihelium-3, which propagates then in our galactic magnetic field, and it can reach Earth environment. And then here, hopefully, we could measure it. And indeed, there are space experiments which are looking for this antihelium-3. There are several. I show example only of one today. It's called Alpha Magnetic Spectrometer, or AMS2. And you can already see from this sketch that the system is much more complicated than a cloud chamber that looked for a positron. Now, it's extremely complicated because the signals are rare and you want to have very high precision, but the underlying idea of these detectors is always the same. So if we want to look what it actually does, which is shown in this sketch here, it still just tracks your particle. It puts your particle in a magnetic field and it tries to reconstruct its trajectory and also tries to identify the particle to be able to say, is it a proton, is it a helium, is it an antiproton? And the complication with these experiments is also such that if you put it very close to Earth, you have these cosmic rays that come not directly from the galaxy, but that come from the interaction of primary cosmic ray with the atmosphere. And then your signal, the measurements you do, is a mixture of everything. So what you want to do is to put this detector as far away from Earth as possible. So what AMS2 did is they put it on the International Space Station, which you can see in the figure here. So This is just a picture of International Space Station. This is the AMS-2 detector, which is mounted on it. And here you can see for comparison also an astronaut tending to it. So the main goal of this experiment was to measure in general all species of cosmic rays to understand what happens in our galaxy. And this is what it did. It measured yields and also spectra, so it measured also how much energy the cosmic rays that it measures has for many different species, which you can see on the left side. So here you can see nuclear charge on the x-axis and the number of events recorded on the y-axis. And you can see that, for example, for hydrogen, which is in principle a proton, you have more than 1 billion events collected. And then you have many different species. You have oxygen, you have iron, you can have everything. And these are the highest precision data we have to study cosmic rays. And AMS-2 also has some data on this Antihelium-3. What you can see in this plot is, again, in this case, mass on the x-axis. On the y-axis on the left side, you see how much helium you have, so it's order of millions. And this is the spectra of helium, the blue points. The green points are the antihelium events, and the axis now is this one. So they have only around 9 events by the end of 2022. The problem with this data is that it's very hard to separate antinuclei because you have 3 antinuclei and then you have like millions of nuclei. And this data indeed is shown at conferences, but it's not yet published. So that the experiment themselves, they're very careful with it. They're taking now more data, and then at some point, hopefully they publish it. But this, of course, caused a lot of questions in the field, because is this already like dark matter? Are these Antihelium-3 a signal for it? And the thing is that the story is a bit more complicated than I told you up to now. So what I explained to you now is that dark matter annihilates, produce Antihelium-3, and propagates in the galaxy. However, in the galaxy, you also have these protons and helium and other particles that I showed you before, which have very high energies. So what happens is that in interstellar medium, you also have gas. It's very, very diluted, but you have protons and you have helium. And your high energy proton cosmic ray inside of the galaxy might collide with a proton in interstellar medium, and then you produce an Antihelium-3. And this is an ordinary process that we understand and that contributes to the background, as you can see here. Now, the issue is that once detectors measure the particle, they only know it's Antihelium-3 and its energy. They don't know where it came from. So what you measure is basically flux as a function of energy in these measurements. So on the x-axis in this figure, you can see energy. And the y-axis is flux, which basically tells you how many of these particles you see per specific energy, per specific angle, and also per time. So it really tells us how many of them are flowing towards you. And you can see that the full measurement would be the black line, which is the sum of the signal and the background. And if you want to say anything about dark matter, you need to extract the signal, which means you need to know the background, which means you have to understand very well the underlying processes that happens with these cosmic rays. And you can see in this, again, sketch that I showed you before. I will come back to it also very often to kind of have like a ground where we can all meet if someone gets lost. And now the animation is a bit different, because now we look not at different signal and background as themselves, but we really look at the processes. So in the first step, we have to produce the antinuclei, and we have to understand how they are produced. Then we need to understand how they move in the galactic magnetic field and in general diffuse in our galaxy. And then finally, when these antinuclei propagate in the galaxy, they might still interact with interstellar medium and they might disappear. So what happens is that you produce new particles, but your Antihelium-3 is gone. And this, of course, would result in lower flux predictions than if such processes would not happen. Now, the propagation is something which is specific for our galaxy. However, the production and destruction is something we can measure at accelerator facilities. And this is something we need as input for these dark matter searches. Now, where we can do it, there are several accelerator facilities around the world. What I will talk today about is LHC and CERN, because this is where I work. When I was younger, I was ignorant. I'm still now ignorant in many things. And I did not really separate between CERN and LHC. So CERN is the organization itself. It stands for the European Organization for Nuclear Research. So these are the people who have the money, who hire people, who take care of facilities, and who have the facilities such as accelerators. LHC itself stands for a Large Hadron Collider, and this is the machine that accelerates our particles. So it can accelerate protons, but it also can accelerate heavy ions. And within CERN, we just call it the machine because it's the machine that accelerates our particles. You can see that it's a ring. It's a very, very large ring. It basically goes both through France and Switzerland. So I think on the left side, you have the France. And to the right side of this yellow border, you have Switzerland. And it collides these particles at almost speed of light in 4 different parts of the LHC tunnel. Now, you might ask me why we want to look for these antihelium-3 particles, specifically at the LHC. And okay, I also wanted to show how big it would be if it would be on Vilnius. But if we ask the question of why we want to look at the LHC and not other accelerators, because there are pros and cons to look at different places. The pro for LHC is that we collide particles at such high energy that when we produce particles, we produce the same amount of matter and antimatter. And this you can see in this plot where you see antiproton to proton ratio as a function of basically collision energy. It's combination of results from different experiments, and you can see that the higher we go in collision energy, the closer we get to unity. So at the LHC, we really produce the same amount of matter and antimatter, which means we also produce a lot of antihelium-3. Now, if we go back to the LHC, and this is another sketch of it, where you can see that, okay, the tunnel is actually under the ground, just as the 4 detectors. So the 4 experiments that actually measure what happens when the collision is there. Out of the 4 detectors, CMS and ATLAS are the largest one, and they are best known because they are the ones who discovered Higgs. Then you have LHCb, which is looking into matter-antimatter asymmetry, and you have ALICE, which is a bit different than the rest of experiments because the rest of experiments were built to look mainly in proton-proton collisions, but ALICE was designed to look at heavy ion collisions because once you collide them, you create a kind of new state of matter where quarks and gluons are deconfined. And the idea was to observe it and to also study the properties. So from these experiments, if you are interested in LHCb, I take a moment to advertise my friend who came back to Lithuania and opened the LHCb Vilnius group. So if you are interested in LHC physics, you can go talk to him. He's also hiring people. What we will talk today more about is ALICE, because ALICE is actually the experiment I work for. So what these experiments do is that they have these huge detectors which try to measure the particles. And the idea, again, is very similar. What you want at the end to do is to identify the particles and to measure their momenta. So the experiment is huge. It weighs 10,000 tons. It's 16 meters in height. You can see here a comparison to a human being. And it's a system that combines a lot of different detectors. And I don't want to go here into detail, but the most, okay, this is me in front of it. It's very exciting when you are a master student to see these huge detectors. But the main point I wanted to make here is that with this detector, we can measure the particles, their momenta, identify them, and then use these particles to do any physics we want to do. Okay, and this was a bit of going away from the main topic to discuss LHC. But now we come back. So we said we are interested in production and destruction. So what we can do with production is to really measure how many of these antinuclei we produce in specific collisions at LHC. And we can measure what momenta these particles have, which you can see on the x-axis. On the y-axis, you see the yield. So you see how many antihelium-3 you produce per event for specific momenta and rapidity. The different lines, well, the different colors correspond to different types of collisions, which is based on multiplicity. Because when you collide the 2 protons, they can collide in a bit different ways, and then they produce different amount of particles. So you collide 2 protons, and you might produce 5 charged particles, but you also might produce 40 charged particles. And then physics within it is a bit different, and then we can sometimes just do measurements for these different bands to see how much the difference changes, the physics changes. I assume this plot tells you not much because it doesn't tell much to me too. So these values by themselves to me says very little. And then the other problem is that this is measured at LHC energy, which is 13 tera-electron volts. However, in cosmic rays, you have these collisions where the cosmic ray might have any energy at once, basically. It can be 10 MeV, it can be 1000 GeV, it can be many different values, which would mean that to model these cosmic rays, we would need to produce a bunch of different accelerator facilities to measure collisions at different energies, which is not feasible. So what you want to do instead, you want to find a model which you can really, from theoretical point of view, explore, create, and then be able to reproduce the data that exists in the world, and then use it to interpolate between the data that exists. And how the nuclei are produced is actually a completely different topic, which is very widely studied in ALICE. But most of the evidence we see is that most likely what happens with these antinuclei, that they are not produced immediately when collision happens, and you just produce antihelium-3 and it comes out of the collision. What happens is that you produce first nucleons, so your protons and neutrons, which then interact via final state interaction, coalesce and creates the bound state, which is your nucleus. And then you have your antihelium-3. I will not go into the theory details, but if you develop these models, you can predict what you measure at LHC. And this was done in this figure here. So the points are actually the same ones as I showed you before, but before I showed them in log scale, and now it's in linear scale, so it looks a bit different, but it's exactly the same data. And now you see these lines, which explain the data for all the different multiplicity bands very well. So what you can do is you can use then this model and predict how many antihelium-3 you would produce in galaxy in the different energy collisions. And this can go directly in your studies of the cosmic rays. So this is what we can do at the LHC with the production. And then the next question is, can we do with the destruction? So what this destruction means is that your antihelium-3 interacts with the gas in interstellar medium and disappears. What you can do is you can measure in accelerator facilities the so-called inelastic cross-section, which basically tells you the probability that your antinucleus actually disappears. And for antimatter, this is not a very well measured process. So for antiprotons on different targets, we have a lot of data at different collision energies. However, once we go to antideuterons, this becomes very complicated because how people usually do is they take your particle of interest as a beam. So you have to create a bunch of antinuclei, you have to accelerate them and put a target. Now creating an antideutron beam is very hard. For antihelium is almost impossible. So indeed, before ALICE came into this game, there was no data available at all for antihelium-3 because it's really hard to make the beam. But at LHC, we produce a lot of antihelium-3. You saw even spectra measured. So what we need to do now is we know we have antihelium-3, but we have to find a way in our system to measure the inelastic interaction. And how we do it is we basically use our detector itself as a target. So what you can see here is the same ALICE detector you saw before as this huge red object, but from front of it. So you see that the detectors, they are mounted to each other a bit like an onion. So you have in the center the ITS, then you have the TPC detector, TRD detector, and TOF detector, okay? And what you can do to extract an elastic cross-section is you can measure the ratio of how much antimatter you have and how much matter you have. Because at the production point, it should be equal to unity because you produce the same amount of antihelium-3 as helium-3. However, once we measure the ratio, it's not equal to unity anymore because antihelium-3 interacts with helium-3 in a slightly different way. And what you can do is you can measure the ratio, which then will depend on both inelastic interactions for helium-3 and antihelium-3. The helium-3 one you know, and you can extract the antihelium-3 with so-called Monte Carlo simulations. What Monte Carlo simulations means is that we perform a simulation where we implement the full description of our detector. We implement all the interactions that the particle should have with that detector, and then we just shoot a lot of particles in the simulation and we can make statistics out of it. And in these Monte Carlo simulations, you can change physics. You can change an elastic cross-section you can assume, and you can see which one would best agree with your data. We also have a different method to use our detector as a target material, which is a bit easier maybe to understand because it's a bit more similar to this beam and target setup. So what we do is we can measure our particles within the TPC, which is this inner blue detector. We just count them. We say, okay, there are like 50. And then we can recount them with the most outer layer, the TOF, and then we see that, okay, it's only 40. And what happens is that some of those particles interact with the detector material over there inelastically, and they disappear. And from this ratio, we can also extract the inelastic interaction. Now, I said it in a very generic way, and only for this one time, I want to go a bit more into details of the analysis itself to explain what exactly we do. So in the first step, we have to measure the ratio for the first method of antimatter to matter. So we measure the ratio of antihelium-3 to helium-3. And you can see that these values are shown here as a function of moment over charge. And these are the blue points. The vertical lines correspond to statistical uncertainty, and the boxes correspond to systematic uncertainty based on some things we have to assume. We see that it's okay, it's below unity within uncertainty limits, and we see it's compared to this black line first. So what black line corresponds to is result from these Monte Carlo studies where you really simulate your full detector, and you have some sort of theory prediction for an elastic cross-section of antihelium-3. And we see that it's close, but not perfect. And as I mentioned before, what you can do in the simulations is you can play with the physics you have inside. So you can change the inelastic cross-section value by some percentage and see how would your ratio would change. So you really just go into your simulation, you say, okay, my inelastic cross-section is now changed by 50%, what result I get out? And this would be the red lines. Why do we show them here is to really just say that our measurement is indeed sensitive to an elastic cross-section, and we can extract these values. Now, how we exactly extract these values is a process we do on bin by bin basis, which means we take specific momenta of antihelium-3, and for it, we again go back to Monte Carlo, and we do a study where we estimate this ratio that we would expect to obtain as a function of different assumption of inelastic cross-section. We can parameterize this with an exponential. We can take our data point, we can take its uncertainty, and we can see where they would overlap with this curve and which inelastic cross-section value would actually reproduce what we measured, and which values would correspond to the uncertainty. In a more scientific way, the same sketch that I showed you now is shown here in this plot where you really see our data. So this is the first point that you see on this side here. And this is an elastic cross-section we obtain. So we do this for all the bins, and the same method can be applied for this case where you have the TOF to TPC matching, where I said that we really just count the particles at the different detectors, and then we do same game with Monte Carlo. And this allows us to extract the first ever measurement of the inelastic cross-section of antihelium-3. And again, you can see here values on the left side for the first method, on the right side for the second method. The curves correspond to these predictions I showed you before, so we see that here is actually not that far away from the truth. And then we can take this and we can use it for cosmic rays and see what happens. So this brings me back to the sketch I showed you before multiple times. So we discussed now how we can help with accelerator facilities to understand production and destruction of these particles, but I did not discuss the propagation yet. So the propagation is something that you cannot really study at accelerator facilities, but you can model these things. And you can do it by solving the so-called transfer equation, which is shown here. You don't have to read it now. The main point here is that it has three main components. And actually now the animation will remind me the one that I showed you at the beginning. Because what I said before is that we have the production. So now we still have the production, we just put it in terms of math as a so-called source function. Then we have part of equation which accounts for diffusion, convection, and all the other processes in the galaxy. And then finally we have this destruction term where the antihelium-3 interacts inelastically with the interstellar medium. How you can solve this equation is analytically or numerically. If you do it analytically, you have to make many assumptions. So your result will not correspond very much to the galaxy that we live in. What you can do instead is to solve it numerically, for which there are several available codes. One of those codes is called GalProp. It's publicly available, so you can also download it and play with it. And they don't include these antinuclei, so you have to include them yourself. And I want to just show a little bit step-by-step procedure on how exactly we do that. So in case of propagation, it's expected to be the same for all different cosmic ray species. So once you have the AMS2 measurements I showed you before, which I actually shown also here for the different species, but before you saw the yield, you remember this colorful peaks, now you see the actual shape. So you see it as a function of rigidity, where rigidity, you can imagine it corresponds to momenta and charge. So you have these parameters, which are these propagation parameters in front of your different terms in equation, and you fit them such to the available MS data that you can fit it very well. And the fitting results are shown with the red curves. So we can see that the model can actually explain the physics that we already understand very well. And then we can use these propagation parameters to study our antinuclei. Now for the source term, the situation is a bit complicated because we need to implement it for both the case of dark matter annihilation and the case of cosmic ray collisions with interstellar medium. So for the latter, the source function looks like this. Again, you don't have to understand the details, but I find it very nice because it explains very well what happens. So what you need to have is the distribution of gas in interstellar medium, which acts as a target material. You need to know distribution of cosmic rays, which act as a projectile, and once you multiply them, you basically know how many collisions happened in the galaxy. And then you need to know the production cross-section that we discussed before, where I showed you that we can constrain the models with LHC, which allows us to obtain these inelastic production cross-section predictions. We put everything in GalProp, and then we also need a dark matter case. And here the idea of the equation is very similar, because first you really need to understand how many of these annihilations happens in the galaxy, for which you include the dark matter profile in our galaxy, which shows a density distribution as a function of distance from the center of the galaxy. And we see that most dark matter is in the center, and we are at 8 kiloparsecs here in the solar system. This gives a density, which means you need also to know the mass to scale it down, and this depends on specific dark matter model you test. So indeed, if you want to test different models, you have to redo the calculations for them specifically. You need to know the probability that the dark matter particles annihilate, and then finally you need to know how probable it is to produce the antihelium-3, just like in the case before. But here you use slightly different collision data to constrain this term. And with this, we have the source done. We need to include an elastic cross-section. These are the measurements I showed you before. The only complication is that this uses ALICE as a target material, which is very heavy. It's structures from iron and other things. In the galaxy, we have mainly protons and helium. So we need to somehow find a way to scale our results to lighter targets. And we do this by employing, again, these Monte Carlo simulations with theory predictions, where we basically correct the model. And then we see its prediction for the inelastic interactions on proton and helium-4 gases in the galaxy. And now we have all the terms. So now we can look at the predictions for the actual fluxes. And before I show that, just a small note is that just the same way as Earth has a magnetic field, Sun has it too. And also Sun has these little explosions and other things that affect cosmic rays. So if you want to compare the predictions to the experiments that are happening within solar system, you have to account for it. And for this, there are some models, which I don't want to explain. I just want to mention that this is something that is also a study by itself. And then you can look at final fluxes. So this is the final result of such studies, where you see prediction of antihelium-3 flux as a function of the kinetic energy per nucleon. The red line corresponds to what you would expect if you would obtain antihelium-3 from dark matter. The blue line corresponds to the background if it comes from cosmic ray interactions with interstellar medium. And we see that we have very good signal to background ratio at low kinetic energy, which is why these antinuclei are seen as a very nice probe, indirect probe for dark matter. Now you also see the different lines. You have the dashed line, which corresponds to the flux which you would obtain if there are no inelastic interactions in the galaxy. And the solid line and band corresponds if you include them properly, and we see the fluxes are less, as one would also expect. Now what one can ask themselves is how much we actually lose, and for this we define the variable called transparency, which you see in the lower part of the plot, which is the ratio of flux obtained with specific inelastic interactions and flux obtained if all the particles would survive the journey in the galaxy and would reach Earth. And we see that for the antihelium from dark matter, around 50% survive, while for background, around 25 to 90% survive. Now, these are rather high values, and what it means is that these antinuclei could really reach our detectors, and they can be used as a indirect probe for the dark matter. These can also be used in all the future studies, the measurement that we did by ALICE. And the other interesting thing is we can compare these fluxes to sensitivity limits of detectors. So GAPS is a cosmic ray detector I did not tell you today about, but they're aiming to get the low energy antinuclear fluxes. And we see that for our predictions, they would not reach the fluxes. And this is the same sensitivity thing for the AMS, the detector I showed you at the beginning. And we see that it also does not really reach these values. Now, I said that IMS-3 has these 9 candidates, or at 2022, they had 9 candidates of antihelium-3. So where do they come from? So their energy that they measure is approximately at this value where we see we are order of magnitude away. And this is another question which people are trying to work a lot on, and I just want to show very shortly one last slide. The idea here is that maybe the antihelium-3 is produced not directly from dark matter annihilation, but you could, for example, produce heavier hadrons, such as lambda sub b particle, which is a baryon, like a proton. It means it consists of 3 quarks, but one of those quarks is a beauty quark, which is very heavy. So this one particle weighs slightly more than the full antihelium-3 nucleus, and it could decay into it. And then what the theory people said, if in this process, what could happen is that your produced antihelium-3 gets higher energy. It gets a bit boosted compared to direct production. And you also get higher fluxes. The problem is that this lambda sub b decay into antihelium-3 was not known at all until very recently. So all of this were a bit like magic games. You can increase values and kind of guess things. And this is just another time to say that once we have these predictions, we need experimental proof that this is something that could really happen. And this process is something that LHCb works on. So if you want to discuss a bit more about it, you could talk to Mindaugas if you are interested. And this is the summary. Instead of summary, I just want to show I want to show short video, which, okay. It's a summary of my talk in 3 minutes. And hopefully now you can follow it. Okay, what happened? I didn't do anything. Now everything is black. Okay.
Some of the building blocks of our galaxy still remain a mystery. We know that only a small fraction, about 15% of the matter in our universe, is the normal known matter. What makes up the rest? We assume that 85% of the mass in our galaxy consists of hitherto unknown particles. Since they are invisible and their nature is unclear, we call them dark matter. We know dark matter exists because we see its gravitational effects. Physicists try to research dark matter with many different methods. One of them is the observation of antinuclei in cosmic rays, since those can be produced in the collisions of dark matter particles. However, they can also be produced in a collision of cosmic rays with normal interstellar matter. But those antinuclei have a much higher energy than the ones produced from dark matter, so we hope that they can be well differentiated. An important antinucleus is antihelium-3. It has the same mass as regular helium-3, but the opposite charge. The AMS experiment on the International Space Station is already searching for them in space, and the balloon experiment GAPS will fly over the South Pole in late 2023 to extend the search. Antihelium-3 particles in cosmic rays are produced at distances up to 10,000 light-years away. But we don't know how much antihelium-3 gets lost on its long way to Earth. How can the rate of survival be measured? For this, we use the Large Hadron Collider at CERN in Geneva, where all kinds of particles are produced. Yes, the LHC is an antinuclei factory, and the ALICE detector is specialized in the identification of nuclei and antinuclei. Here we collide either lead nuclei or protons and observe the produced antihelium-3 nuclei. We use the ALICE detector at the LHC to measure the probability for antihelium-3 to collide with matter particles and disappear. Because exactly like the interstellar medium, the detector is made of normal matter. The result: about half of the antihelium-3 flying towards Earth from our galaxy survives the long journey. Their observation in cosmic rays will be a breakthrough on the basis of this research. We can now better interpret future observations of antihelium-3. And maybe we could finally solve the mystery of what our galaxy consists of.
Okay, that's it. Thank you for your attention.
Okay, thanks for the nice talk. So I think the interhuman medium is now transparent to questions.
There is a question there.
Thank you for your presentation. I have one question. How do we know that dark matter interactions will produce antihelium-3? Is it based on some model of dark matter or some candidate for the particle of dark matter?
So we don't know in principle. There are many models, so we don't even know if dark matter could at all interact with standard matter particles. But it's a little bit of a problem that if you say that there is no way that it interacts, you cannot observe it. So what most theorists do, they assume that the particles interact very weakly, like the weakly interactive massive particle model. And in those models, you indeed see that it should couple to standard model and could annihilate. But then there are also some theories which would say that, okay, they cannot annihilate and produce the antihelium-3. So it's a bit also of a sense that if we don't see it at all at the end, after 15 years, when we have like high precision measurements, it doesn't mean that dark matter does not exist. It means that if it exists, it could also just not have this process happening at all.
Okay. Thank you.
Yeah. Okay.
No more questions, really? Okay, if not, then let's thank Laura again.